Hello Internet. This is part 2 of my videos on the preliminary mathematics of cryptology. In this video I'll be going over Euclid's algorithm and the greatest common divisor, and in the end I'll briefly touch upon the multiplicative inverse of a modulo b and b modulo a. So let's get started. The greatest common divisor, or the GCD, is the largest value that divides two numbers, a and b. Note that the greatest common divisor of a and b is the same as the greatest common divisor of b and a. The way we're going to find the greatest common divisor is by using Euclid's algorithm. I'm going to write that here. If you watched my previous video, each iteration in the algorithm is going to look very familiar because it's going to be long division at each step. Recall quickly that a number b divides a if there exists an integer c such that a is equal to b multiplied by c. And if this isn't the case, then we can write up a as a product of b and c plus some remainder value that we find that added on to b multiplied by c will equal a. In the previous video, we called c the quotient, q, and r the remainder. So let me write that quickly. So we actually had a equal to b multiplied by q plus r. In Euclid's algorithm, we start out by assigning a to a value called remainder 0. And then we assign b to be remainder 1. And then we express remainder 0 in terms of remainder 1. So we write remainder 0 is equal to remainder 1 multiplied by quotient 1 plus remainder 2. We discover remainder 2 by subtracting remainder 1 multiplied by quotient 1 from remainder 0. And so we discover remainder 2. And then we express remainder 1 in terms of remainder 2. So we say remainder 1 is equal to remainder 2 multiplied by quotient 2 plus remainder 3. And we continue like this until we hit a remainder I that is equal to 0. And once we hit a remainder that is equal to 0, we take the previous remainder, and that is the greatest common divisor of a and b. So in a sense, we could write up that the greatest common divisor of a and b is equal to remainder I minus 1. I'm going to go through 3 examples with numbers, so you actually get a real feel for how the algorithm goes. So let's write a line here. And the first example I'm going to go over is a really simple one. I'm going to say a is equal to 9 and b is equal to 4. So we're trying to find the greatest common divisor of 9 and 4. And the way we do that is we say that remainder 0 is equal to 9 and remainder 1 is equal to 4. And then we say that 9 is equal to 4 multiplied by 2. 4 goes into 9 twice. 4 multiplied by 2 is 8. So the remainder is 1. So we take 1 down as remainder 2. And then we express 4 in terms of remainder 2. So we have 4 is equal to 1 multiplied by 4 plus 0. So remainder 3 is equal to 0. So now we've hit a remainder that is equal to 0. And so we take the previous remainder, which is remainder 2, because remainder 3 minus 1 is equal to remainder 2. The value of remainder 2 is of course 1, so the greatest common divisor of 9 and 4 is equal to 1. I'm going to go through a longer example down here. In the next example, we are going to try to find the greatest common divisor of 90 and 34. If you have the book Cryptology and How to Crack It, this is example 241. So let's get started. We start out just as before with remainder 0 equal to 90. And remainder 1 is equal to 34. 90 is equal to 34 multiplied by 2. 34 multiplied by 2 is 68. 90 minus 68 is 22. So the new remainder we find is 22. So we take 22 down as remainder 2. And then we express 34 is equal to 22 multiplied by 1 plus 12. Remainder 3 then is equal to 12. 22 is equal to 12 multiplied by 1 plus 10. We find remainder 4 to be 10. 12 is equal to 10 multiplied by 1 plus 2. So remainder 5 is equal to 2. 10 is equal to 2 multiplied by 5 plus 0. So remainder 6 is equal to 0. And again, because we've now hit a 0, the answer is the previous remainder, namely remainder 5. And so the answer to the greatest common divisor of 90 and 34 is equal to 2. I want you to notice here how this is just a semantic trick to remember how the algorithm works, or what each step of the algorithm looks like. I want you to notice how the remainder that we find in each step trickles down to first become the value that we express the following remainder as, and then itself trickle down to become a new remainder that we need to express with the remainder that we find in the previous line. So you can see 22 trickles down to help express remainder 1, but then it itself is remainder 2 that we need to express through the remainder that we find in the equation for remainder 1, namely 12, which follows the exact same pattern, trickling down to help express 22, and then down once again to become the remainder we need to express. And the same goes for 10. It helps to express remainder 3, and then itself became remainder 4. Notice also how the remainders that we find over here are strictly lesser than the previous remainder that we found. And this is our guarantee, so to speak, that the algorithm will terminate, because the values are approaching 0 and will eventually hit 0, meaning that the algorithm will terminate. I'm going to go through one more example, but I'm going to write it up slightly differently. And the reason for that is I want you to be familiar with the way of writing it up, because in a future video I'm going to go over Euclid's extended algorithm for the greatest common divisor and for finding the multiplicative inverse of a modulo b and b modulo a. So let me go to the side here. Don't worry if you don't know what the multiplicative inverse is. I'm going to explain that in the next video. In this example, we are trying to find the greatest common divisor of 55 and 34. If you have the book Cryptology and How to Crack It, this is example 242. And the way we're going to write it up is we're going to start by writing I, which is our looping variable. Then we're going to write remainder I, which is going to be the remainder in each step. We are going to write quotient I for the quotient in each step. And just to finish the tabular format here, we're also going to write S, I, and T, I. These two variables, Si and Ti, you don't have to worry about right now because we're not going to go over them. I'm just going to write it up here to show you that they will be included in the table in a following video. Let me just see if I can draw a straight line here. Well, good enough. So let's start here. At step 0, we have remainder 0, which is equal to 55. At step 1 here, we of course have 34, which is our remainder 1. 34 goes into 55 once, and the remainder we find is 21. Notice here how I am writing the remainder and the quotient on the same line, and I'm not writing 55 expressed as a calculation of 34 multiplied by a quotient plus a remainder. This is deliberate because we're going to need those values for SI and TI later. But you can easily see here that 34 goes into 55 once and the remainder is 21. "21 goes into 34 once and the remainder is 13. 13 goes into 21 once. The remainder is 8. 8 goes into 13 once. The remainder is 5. 5 goes into 8 once. The remainder is 3. 3 goes into 5 once. The remainder is 2. 2 goes into 3 once. The remainder is 1. 1 goes into 2 twice. And the remainder is 0. And so our answer is, of course, remainder 8, which is equal to 1. So the greatest common divisor of 55 and 34 is equal to 1. Now, here's a quick note. If the greatest common divisor of two numbers, a and b, is equal to 1, we say that those two values are co-prime. This co-primality property is really important for cryptology. And the reason for that is it reveals to us that the two values a and b have a multiplicative inverse modulo each other. So there's a multiplicative inverse of a modulo b and b modulo a. The way we write that is we write a to the power of -1 modulo b. This is the multiplicative inverse of a modulo b. We write b to the power of -1 modulo a, which is of course the multiplicative inverse of b modulo a. In our example, that would be 55 to the power of -1 modulo 34, and 34 to the power of -1 modulo 55. So these here, a to the power of -1 and b to the power of -1, are the multiplicative inverses. In the next video, I'm going to show you what the multiplicative inverse is and why it's important for cryptology. And in the video after that, I'm going to show you how to find the multiplicative inverses of a modulo b and b modulo a using Euclid's extended algorithm.